telling you all about chi-squared distribution for further maths A-level. We're going to be looking at it for modelling and for test for independence. The test for independence being the main one for the first part and the modelling for the second. So basically, when you've done the binomial and the Poisson distribution, you've often been asked whether the distributions are good models to use for the data that you've been presented with. And you've mainly done that by eye so far, especially with the Poisson that we covered earlier in the year. Whereas really we need to know significantly whether it's a good model, and the chi-square distribution can do that for us. So you'll be able to calculate the expected values based on the Poisson formula, and then we will put them into the chi-squared statistic, which you'll see is a connection between the observed values and the expected values. But we also use it as a test for independence. So right back in the days of year 9 and 10, when we did probability and we used the AND principle, we would say that the probability of A and B occurring is the probability of A times the probability of B. And we assumed that the events were independent for us to be able to do that. Well, we can sort of use that in a roundabout way. We can see whether two variables are independent, because we can then say, right, okay, let's assume they are independent. I'm going to work out the probability of variable A happening and variable B happening and see if it ties in. In other words, if they are independent, you would assume that the observed and the expected values will be similar, statistically similar, and the chi-square test can look at how similar they are and determine whether it is significantly so or not. It's a quite nice distribution. It's not difficult to apply. It's probably more time consuming than anything. So the process is that we are going to be working out the probability of A and B for the variables we're given, and we're going to have a table of observed values. This must be the case, that we've got observed values that have been gathered. Then we're going to calculate the expected values, assuming independence, so using this P of A and B equals P of A times the P of B. And then I'm going to work out the chi-squared statistic, which is, it's the observed value minus the expected value, all squared, and we square it because obviously that would be negative otherwise. And then we divide it by the expected value. So it's a bit weighted towards the expected there. But that's how the chi-squared statistic works. Then we're going to find a critical value from tables, which are always given to you, and we will reject H0 when our calculated chi-squared value, so our test statistic, is greater than the critical value. And so basically, if you think about it in terms of discrepancies, the bigger the discrepancy between the observed and the expected, then the greater the want to say that they are not independent is. So in other words, if they are both quite different, then we can't be assuming that the two variables are independent. So we reject H0, we reject the assumption of independence if our value is greater than the critical value. When we reject H0, if we reject H0, it's really important to go back to the tables and see, what caused it to happen. It won't necessarily be every cell or even every row within that cell. It could be particular areas, and it's important that you look to see which areas it actually is that is causing this discrepancy. We work out degrees of freedom. Basically, you'll see in the process we're about to do that some cells are easily worked out when I have some other bits of information. So the degrees of freedom looks at like the independent cells that are available to us. Generally, all you need to know is that for an n by m table, then the degrees of freedom is n minus 1 times n minus 1. So in other words, if it was like a 5 by 8 table, then it would be 4 times 7 is 28, 28 degrees of freedom. Generally, I mean, because this is impractical in an exam, we tend to look at like 3 by 3s, 3 by 4 tables, or 2 by 2s, as you'll see. Now, a couple of vital points that are easily forgotten, especially when you're in an exam, but they must be carried out. If your expected cells are small, that is, that they're less than 5, then you've got to combine cells because they become meaningless. But you should only combine neighbouring cells that make some kind of sense with each other. So if it was like age, and you had 19 to 30, 30 to 40, and then 40 to 70, and you didn't have too many in the 30 to 40 bracket, then you couldn't combine that with the 19 to 30. It'd be stupid to combine the 30 to 40 with like 0 to 10 or something. It's got to have some connection between the two. So neighbouring cells can be combined. And that's really important. It will be a trick question that they'll assume you're going to do that, so please check it. Now this is important. If you look up Yates correction, you'll find that there's a lot of statisticians out there that assume Yates correction is optional, and in reality maybe it is, but as regards your exam, carry out Yates correction. And basically you carry it out on when you've got a 2 by 2 table, because you've got so few independent cells. It needs to sort of have a little correction to take account of that. And the only difference is that when we do observed minus expected, we ignore the sign, then we take off a half, and then we square it. So if my observed was 10 and my expected was 12, 10 take away 12 is minus 2. Ignore the minus, so I've got 2. Take away a half is 1.5, and then I square it, 2.25. Okay, so that's the Yates correction. Again, they will not tell you to use it, but they will assume you are using it. So it is important, and that's come up on many an exam now. And you do that for all of the 4 cells that are contained. I mean, luckily, because there's only 4 cells ever going to be there, because you would only do it on a 2 by 2, it's not such an onerous task. But as I say here, there are arguments for and against it, but for you should be using it. This is just a little aside. I've talked about this in normal maths before. When we're looking at the sample data, we tend to use Roman letters, and when we then refer to the population, we use the equivalent, or it generally is the equivalent for the Greek letter. But with chi-squared, who have we got here? There isn't really a Roman equivalent to chi, so chi-squared, or chi is the letter itself. So it is the sample, it sort of looks like an X. So when we look at the sample statistic, it's like an X squared, and then you can see the slight variation here with the curl. Just in case you can't see where my cursor is, just here. It's got like a slight curl to it, but we'll know what you're talking about if you do that. The hypotheses are pretty much all the same, must be written properly. We say the H0 such that the variables A and B, and it's important to say them in context, are independent, so we assume independence. Sometimes you'll see it written as there's no association between them. So there's independent there, that's our null hypothesis. And then the alternative hypothesis is that A and B are not independent, or there is association between them. Okay, so this is a wordy one, there's no formula in there. So here's an example that we're going to look at in detail. The manager of a restaurant undertakes a survey of the numbers and types of drinks ordered by a random sample of 400 customers. And you can see the 400 here. Let me just put that in just again in case you can't see. Yep, 400 there. Customers are categorised as either business, tourist or local. So business, tourist, local, and the drinks are categorised as alcoholic or soft drinks. And a table of results of the survey is as follows. Carry out Test at the 5% significance level to examine whether there is any association between the type of customer and the type of drink. State carefully your null and alternative hypotheses. Look, there's 10 marks for this. They're not breaking it down for you. You need to know how to do a full test on this. So what we're looking at is these were the observed values that the restaurant manager took. So business customers came in, and we had, out of 117 business customers, 54 had an alcoholic drink, 63 had soft drink. There were 136 tourists, 95 had alcoholic drinks and 41 soft, and then there were locals, 71 had alcoholic drinks and 76 had soft drinks. Okay, and these are your totals for each of those columns and rows. Your hypothesis is that there is no association between the type of customer and the type of drink. And then H1, there is association between type of customer and type of drink. So what I'm going to do is break this task down and show you the steps to follow. We've already done our hypotheses, we've already stated them. And what we have in the table that was given in the question is a set of observed values. Okay, these are very important, we need these. And I've said here, always make sure that the rows and row totals and column totals are worked out. These here, here and here. These are called the marginal totals. You need them because actually we are not going to use these cell values at all in our calculations. We are going to use these row totals and column totals, so it's important that you have them. And we're going to work out the expected values just like we normally do really when we do expectation is NP, but we've also got two probabilities that we've got to combine. So I want to work out what the expected value is for this cell here, the business and alcoholic drink. So that's the probability of being a business person and having an alcoholic drink. Now remember, we're assuming independence here. We have to assume independence. So that must be, based on our laws of probabilities, the probability of being a businessman, 117 over 400, multiplied by the probability of having an alcoholic drink, 220 over 400. So that's the probability. So there. And remember, expectation is probability times n. There were 400 people altogether. 400 times the probability gives me an expected value of 64.35. So I expected there to be 64.35 businessmen who had an alcoholic drink. I observed 54. So straight away I can see it's quite a few more were expected than were actually observed. And you do that for each of the 6 cells. So you'd be probability of being a businessman, 117 over 400, times the probability of having a soft drink, 180 over 400. And here we go. These are all my observed values now, and I can see that expected values here, sorry. I expected 52.65 businessmen to have a soft drink, but I observed 63. Okay, I expected 64.35 businessmen to have an alcoholic drink, but I observed 54. Now, as I said, you could look at these by eye and make a decision, but it's very important in statistics to do things significantly. So we have our expected values and our observed values. Okay, now I've said here, we've worked out our expected values using the probability of A and B being the probability of A times the probability of B. We never use the cell values, we always use the marginal totals. In other words, in all my calculations for the chi-squared statistic, these numbers here, 54, 63, 95, 41, 71, 76, they're not used to work out the probabilities I'm only going to be using those in a little while when I look at every individual cell. To get the probabilities, we use the marginal totals. Okay, and that's really important. Now, I did say here, and this is a little bit about the Yates, like it sort of comes into the Yates correction thing. We could have worked out the last value in each row or column by subtracting the values so far in each row from the marginal total. So for instance, if you add 64.35 to 52.65, you get 117. If I add 74.8 to 61.2, I get 136. If I add these to 64.35 and 74.8 to 80.85, I get 220. So once you've worked out all bar one of any row, you can work out the last one just by subtracting it from the marginal total. Okay, and that's what we mean by independent cells. I didn't need the last cell's bit of information to work it out, because I can work it out from the marginal totals, and that's where degrees of freedom comes in. So we're going to be looking at calculating the test statistic now. This is where the laborious, time-consuming work comes in. I told you what the value was. Epsilon means sum, so we're going to add up all the different observed minus expected squareds over expected. I've given you the answer here first, but I'll show you, I'll bring everything up just so that you can see. So these were the 6 cells, observed, expected, I squared my answer and I divided by the expected. And that's what I got every time when worked out. And this contributed to a chi-squared statistic when I add up all these of 18.4887. Okay, so that's my overall, let's call it a discrepancy as such. These here, you really do need to write them down. Get a lot of people who try and do this all in one go on their calculator, and that's bad, because you're going to have to refer to these. So you see how much time it takes you to do them. You don't want to have to do them again when it's called for later on in the question. So do make a note of them. I often put them in the table when I've worked out my expected values. I often put them in there just so that they're recorded. Now this table is a 3 by 2. There were 3 rows and 2 columns. So my degrees of freedom are 2 multiplied by 1, which is 2. Degrees of freedom, 2. So I go to my table. Oops. And there's the degrees of freedom 2. Now I wanted a 5% significance level. And the way this works is it sort of works with the area to the left. So I'm looking up 0.95. A 1% significance level, you'd look up 0.99. So that's the sort of thing we're looking at. And it's just hidden under here, but that's 5.991. Okay, so that's my critical value. Our test statistic was 18.4887, greater than the critical value, which means there's evidence to reject H0, the null hypothesis, which means there is evidence of association between type of customer and type of drink. Okay, so if you think about it and logically, the discrepancies overall between the observed and expected added up to way more than what was going to be allowed. So therefore, we say no, there is some association going on here. Now, although it didn't ask for in this question, when we reject the null hypothesis, we do often get asked to look back at the cells that contributed mostly to this test statistic. And there's a number of reasons to do this in reality. It could be that you've maybe combined too many groups. I mean, it's like you looked at 3 different types of person coming in. Maybe you should have took non-drivers out of the equation for the businessmen, because obviously if they're driving, they're not going to have an alcoholic drink. And maybe sometimes it's to do with the fact that you've scattered your age ranges too much, or maybe grouped them too much. But in reality, the most important thing is we want to know, which is the actual major part of this that we need to focus on. Maybe we need to look at tourists. Why are tourists having more alcoholic drinks than soft drinks, or the other way round, things like that. So basically what you want to be doing is looking at the cells and picking out all the differences between observed and expected. Okay. You need to look at the ones where the contributions were high. I generally look at ones over 1 if your critical value is low. But if your critical value is quite high, then you could probably, you might sort of think, well, 1 to 1.5 is okay. But use your common sense. It's pretty straightforward. So for me, what I've said, this is a typical explanation. The main contributors to the test statistic were with the tourists, and they had more alcoholic drinks observed than were expected. So we expected 74.8 but observed 95, and that led to a contribution of 5.4551. Whereas for soft drinks, fewer were observed than expected, and I've explained the contribution. And I've done that for all of them. For businessmen, it was the reverse. Fewer alcoholic drinks were observed than expected, but more soft drinks than were expected. And then I've talked about the contributions, and I've said locals followed a similar pattern to businessmen. And see how I've stated all the values here? You have to go with what marks are in the mark scheme. I always err on the side of caution. I'm not going to lose marks if I state too many figures, but I might lose marks if I omit them. So therefore, it is worth highlighting the figures that you're referring to. It doesn't take long. And I've sort of focused mine on the different type of visitor to the establishment. So I've looked at tourists, then businessmen and locals. I could have just looked at it in terms of alcoholic drinks and soft drinks and compared it that way. But you can see the idea here about saying whether more were observed than expected and looking at what actual contribution it was. Okay, so another way we can use chi-square testing is to see if our model is a good match, should we say, so it's a goodness of fit. And what we're going to again be doing is looking at observed and expected values and comparing them. But this time we will find the expected values by using the distribution itself. And then we will, it's like as in if it's a binomial one, we'll use the binomial distribution to find the values. If it's a Poisson, we'll use the Poisson distribution to find the values, and so on. So I said here in statistics there are many distributions, and we're always aiming to find the best, to fit the best model to the data. And the chi-square distribution is used to test whether the model is a good fit or not. Now here's an example with the uniform distribution, and this has come up quite a lot in exams of late. I guess because it's easy to calculate the values without it being too time consuming. So we've got here, Thomas believes he can influence the score on dice when it is rolled. He rolls it 120 times and gets the following results. Okay, so he gets a 1 30 times, 2 24 times, and so on. Do these figures provide evidence at the 1% level that Thomas influenced the outcomes? Now, I've said here that Thomas is not claiming any particular number's going to come up. It's just, that he's just saying he reckons he can influence the dice and almost, see how it's going to move. And as it's a dice, we can easily work out the expected outcomes because it's a uniform distribution. There are 6 possible outcomes. It's thrown 120 times. So therefore, I would expect to get each of those numbers 20 times. And as I've said there, you can't just reject or accept based on whether by eye your values match. You have to carry out the test to see if it's significant or not. Now the null hypothesis is that the probability is a 6th for each outcome, and the alternative hypothesis is it's not a 6th. It could be lower or higher. But I could have read H0 such that Thomas has no influence on the dice, or there's no association between the outcome and Thomas's prediction, or H1 such that there is an association, or not equals 6 here. So you can put it into words. You don't have to do it as a binomial probability thing there, but you can, if you want, instead put it into words. So H0 such that there's no association between what Thomas predicts and what happens. H1 such that there is some association. Again, we're going to use our normal chi-squared statistic, and actually I think this is probably easier than doing it the normal chi-squared way when you've got to use the probability of A times the probability of B. I think this saves is a lot quicker to do for the uniform distribution anyway, and that's a reason why I think it might be that they use it. So just taking one of these, so the observed was 30, the expected was 20, 30 take away 20 is 10, 10 squared is 100, 100 divided by 20 is 5. So we add up all the individual contributions and I get a chi-squared of 11.5. The degrees of freedom in this case are going to be, there's 6 possible things there, 6 possible outcomes, but we always take 1 off. So that leaves us with 5 degrees of freedom. We take away 1. Okay, so it's the degrees of freedom is going to play a major part in what we're doing over the next few slides. And please pick up on how I'm calculating the degrees of freedom in each case. There was nothing else predicted here in terms of any estimating of any parameters. These 20s were worked out accurately based on the assumption of a regular dice. The only thing we have to do for the degrees of freedom is take the 6 categories and subtract 1. It's worth noting, have a quick check to make sure none of your expected cells are less than 5. In this case there are none, so I don't need to do any combining. So I've got 6 at the start, I've ended with 6 at the finish. I just take off 1 because in all honesty I didn't need to work anything out for the last cell. That's always the independent one. So it's easy to work out. So just 1 take away 6, or 1 from 6 to leave 5 degrees of freedom. If I look this up on the table, I haven't put the table up here again, but if you flick back for 1%, remember you would look up 99, look that up and you'd find critical value of 15.09. Our value isn't near 15.09, so there is no evidence to reject H0. In other words, Thomas has no influence on the dice. So I've said here, for the degrees of freedom, for goodness of fit tests, you must carefully look at them. Very, very important. The degrees of freedom, if you get that wrong, you can mess up your whole calculation. You start with the number of classes, so like the number of columns that you're working with, and you subtract 1 for every restriction. So the first one we always subtract is the one that we subtract because we know how to work out the last value. So we always subtract 1 regardless. But then there are other restrictions, like in a bit we're going to do a Poisson calculation where we're going to estimate the mean, and therefore that's a restriction. So if you are not being given a parameter, if you have to calculate it yourself, that then becomes an estimated parameter. And if that's the case, then you take off 1 for that as well. You might also have to take off 1 if you've combined cells. But the easiest way to look at that is don't do the degrees of freedom until you've seen how many cells you've actually ended up with after doing all your combinations. Then you take off 1, then you take off any estimated parameters from there. Okay, so be careful with the binomial and Poisson. You're not going to have to take off any estimated parameters for the uniform distribution because there's no parameters on that. But the only thing you have got to watch out for there is when any cells are less than 5. But then if all the cells are the same, they'd all be less than 5, so that's probably not going to happen either. Okay. So I'll just repeat there, expected frequencies must be 5 or more. So this is a typical Poisson question. We're going to be looking at a number of calls to a counselling service that we assume to be modelled by the Poisson distribution. And we're going to test at the 5% level whether the Poisson is a good model or not. Notice how I've been given the values, and I'm going to have to work out my mean from those values. That means it's an estimated parameter. Also remember, Poisson is infinite, so when I work out this last one, I have to refer to it as 6 or more, not 6. Okay, so that's important as well. Lots of little things from previous A-level topics come creeping back in. So H0, such that the number of calls can be modelled by the Poisson distribution. H1, such that the number of calls cannot be modelled by a Poisson distribution. Always look carefully at the question to see what's a good way of representing the hypotheses. Okay, so we know how to work out the mean of a data like this. We would go 0 times 6 plus 1 times 13 plus 2 times 26 plus 3 times 14 plus 4 times 7 plus 5 times 4 plus 6 times 0, and then we will add them up, divide by 70. So that's going to give me the mean, which is my parameter for lambda, which is the Poisson distribution parameter. So that's been estimated. I then will use that to work out my expected frequencies, but remember that this should be 6 plus at the end. Okay, so my mean was 2.214, so that's lambda. Now, I work out the probability of getting 0 using e to the minus lambda, and then I multiply that by 70, and that gives me an expected value of 7.65. The probability of 1 is e to the minus lambda times lambda, or just leave your original value in, the original probability, and times it by lambda, so times it by 2.214. Remember, this is a recursive formula, so if I know probability of 1 to get 2, I multiply the probability of 1 by lambda over 2, and then I multiply that by lambda over 3 to get 3, lambda over 4 to get 4, and so on. And the expectation is all those probabilities multiplied by 70. However, for the last one, all I have to do was do 70, take away the previous 6 values here, and I could get the 1.79. Or I can do it based on probability, 1 minus all the other probabilities, and then times that by 70. Okay, so I didn't go into much depth of that. You've not long done Poisson distribution, and so that was just the process used to find the expected values. In fact, you did a similar question on that in the Poisson. Now then, the last 2 cells are too low. They are less than 5. If just one of them had been too low, we still combine 2 cells. But in this case, I need to combine both cells, 5 and 6 plus. So that's going to become 5 plus instead now. So now I've gone down to 6 groups. So my degrees of freedom straight off has gone down. I'm going to take 1 off for the fact that you always take 1 off anyway. And then also I'm going to take 1 off for the estimated mean that we have to do. But I'll come to that in a second. So then all I have to do is, there's my observed frequency of 6, my expected frequency is 7.65, I subtract and then square and then divide by the expected, and I do that for all of them, add them all up, and that gives me a chi-squared statistic of 4.404. Now, degrees of freedom. So looking at this table here, I've got 6 classes. I take off 1 because I always do, it's the restriction of the total, but then I have to take off another 1 because I estimated lambda. If they'd have told me at the start lambda's 2.214, then I wouldn't have took 1 off. I was given it, I wouldn't have needed to, but you have to when you've estimated. So my degrees of freedom have gone down to 4. For 5% level, degrees of freedom 4, my critical value is 9.488. My value is not more than that, it's lower than 9.488, so there is no evidence to reject the null hypothesis, and so the Poisson distribution appears to be a good model. If you're ever unsure, do I reject or not, what does a null hypothesis mean? Basically, think about it. If we're saying it's a good model, then we're saying that the observed and the expected should match up with each other. In other words, the discrepancies shouldn't really be there. There shouldn't be too many discrepancies between the values. So therefore, your null hypothesis is assuming that the model is a good fit. So if you've not rejected H0, if you've accepted H0, it means you've accepted that the model is a good fit. Okay, so here's a good example for the binomial distribution, and like we said with the Poisson and the uniform distribution, we're just going to test whether it's a good fit, whether the model works or not, and we're going to use our observed and our expected values. In this example, we've got 10% of people is believed carry a particular genetic defect. Now straight off I can see that they've given me the parameter P, so therefore I'm not going to be estimating that, which means that's going to affect my degrees of freedom because I'm not going to subtract an extra one. Okay, so a new and simple test becomes available to determine whether somebody is a carrier of this defect using the blood specimen. As part of a research project, 100 hospitals are asked to carry out this test anonymously on the next 30 blood samples they take. The results are, and you can see what they are. So this is a binomial distribution with 30 being n, and the probability of a carrying defect is 0.1. So here it's saying out of the 30 samples that one of the hospitals took, that the hospitals took, 11 of those hospitals have no positive tests. Okay, out of the 30. So out of the 30 tests that the hospital took, of those 100 hospitals, 29 had a positive test, 1 out of the 30, and so on. Okay, I mean, so this number of positive tests could have gone up to 30, but clearly it wasn't worth it because only one hospital had more than 7. Okay, so you've got to remember when you're doing the binomial for this that n is 30 and p is 0.1 or a tenth, and when we get our expected values we're going to multiply the probability by 100 in order to get the expectation. Okay, so we're going to test at the 5% level whether 10% of the population carry this defect. So the null hypothesis is that the 10% of people carry the defect. The binomial distribution is appropriate. So the model that 10% of the people carry the defect is appropriate. In other words, H0 such that the model is good to go. It's a good model to use. H1 such the model is not appropriate. Okay, it's always the same sort of thing. H0, we assume everything's okay. Yeah, you're right. You're good to go. Use the binomial. H1 such that you're not. And as said before, the degrees of freedom, the number of classes, at the moment that stands at 8. That might not be the case in a minute. You subtract 1 for, or as we always do, for the number of independent cells, and then we are not going to subtract 1 for any estimated parameters because it's been given. Okay, so in a minute we will calculate our expected frequencies. For this first one I'm going to be doing 30 choose 0 times 0.1 to the 0 times 0.9 to the 30. I'll get my probability, I'll then times it by 100, and that will tell me how many of the hospitals I expected to observe no positive tests. Okay, so these figures are a little confusing at times because you're dealing with 100 hospitals, 30 blood samples, but 100 is the number we're going to multiply by to get our expected value. 30 is the binomial parameter, the n. Okay. Okay, so here's what we did. We did 30 choose 0 times 0.1 to the 0 times 0.9 to the 30, and then we multiply that by the 100 hospitals, and we get our expected value of 4.24. Okay, so then for 1 it would have been 30 choose 1 times 0.1 to the 1 times 0.9 to the 29, and again I would have timesed it by 100 because there were 100 hospitals, and then gone from there. Okay, and they're my expected frequencies. Now if you look, I've got too few there in the 0 column and too few in the 6 and 7, so I'm going to combine the 6 and 7 together. I've put 7 plus there, that should read 6 plus, so let me just go over that. Right, so that should be 6 plus, and I've combined the 0 and the 1 together because there was no, I mean, why would you combine 0, 6 and 7 together? That would be daft. So we combine 6 and 7, and we combine 0 and 1. Okay, so the frequency for 0 and 1 observed was 40. The observed for 6 and 7 combined is 2, and now I have my expected frequencies. So you can see that my degrees of freedom is going to change now. I've got 1, 2, 3, 4, 5, 6 classes, and then I'm going to take off my no estimated ones, take off my usual 1. Okay, so when I work out my chi-squared statistic, I get 39.74. And my degrees of freedom, I've got 6, take away 1, because there are 6 groups in the final combined cells. Take away 1, there are no estimations. Critical value of 11.07, but mine is way more than that. Mine is 39.74, my chi-squared statistic. So there is evidence to reject H0. There is evidence that the binomial distribution is not appropriate for this data. Okay. Explanation. Do go over that again, you know, pause it at times, but really absorb the important points, especially about the modelling. They're not going to give you hints in the question. They're going to assume that you know how to carry these tests out properly. So make sure that you're detailed. Thank you.